before we move on to solving the Monty Hall problem with Bayes' theorem, would you mind just reviewing some of the key lessons that we learned in your previous episode where we talked about conditional probability and joint probability and Bayes' theorem?
Yeah.
Okay.
So let me just rewrite what Bayes' theorem is. Probability of A given B can be rewritten as probability of B given A as a probability of A over all possible probabilities of B. Now, this operates under the definition of conditional probability. So, probability of A given B is probability of A and B over the probability of just B. To continue, before I continue on, I'm no longer going to use the intersection symbol, but another way, just comma. So.
Yep. Those two notations are perfectly exchangeable. Yep.
And the thing is, probability of. So now the probability of A given B, if we were just to do some simple cross multiplication, is just equal to the probability of A and B times probability of A given B times probability of B. That's equal to probability of A and B. Now,
right. So we're simply just multiplying this to here.
Yeah.
Yeah. Okay.
This is also interchangeable. So it's also the same thing as probability of B and A.
Right.
Which this is equal to the probability of B given A times the probability of A.
Right.
So you see where all this is sort of coming from.
Right. So I think it's important to point out here that the this joint probability here is commutative, right?
Yeah.
So let's I think this is a good word. It's commutative. Okay, so the probability of A and B is the same as the probability of B and A. So this operation here on A and B is commutative. Okay.
And with all this is where Bayes' theorem basically comes from, and let's use this now to solve the Monty Hall.
Right. So here you have these two. These two products are equivalent to each other. So all you have to do is divide this by P of B, and you'll get Bayes' theorem.
And another thing before I move on, right now we are only using two random variables. Let's add in a third.
Okay.
Because that's what the Monty Hall problem entails, and let's just sort of prime our audience a little bit.
Okay.
So another way, so the probability of A, B, and C. Now, what I like to do, sometimes if I do get confused with multiple random variables and I want to express a conditional probability using these, I try to group them sometimes as units.
Okay.
So I could also write this as probability of A given B and C times the probability of B and C. Okay.
Here, I'll erase this here. Okay, sorry. Write that again, Arnab. Sorry.
So also equal to probability of B and C. I could also write this maybe as, so let's say probability of A and B given C times probability of C. What else? Do you want to give this a crack, Eric?
We can write it as the probability of C condition on A and B multiplied by A and B. Did you already cover this, or is this is new?
I think this is new.
This is new. Okay. So as Arnab mentioned, you can think of the intersection of A and B as another random variable. So you can think of this as just x, right? So this is just P of x.
So just remember that, because you're going to see a lot of random variables or notation sort of shuffle around here.
Okay.
And with this now, I hope it'll be a little easier to keep track.
Okay. Okay.
Now, let's go to the Monty Hall problem via Bayes theorem.
Okay.